Okay, so always remember in the first step, no, in the alkynation, in the addition reaction of alkene, of water to alkene, no, or water or alcohol to alkene, the first step, there's a zero step for that, which is the protonation of your water to get your H2O plus, no, because this one is your catalyst. And of course, you will have to recover this at the end of the reaction. You'll have your catalyst and you get your H2O plus. You actually have your plus HSO 4 minus. Okay, there is a side reaction. There is a prior reaction prior to the step one where you form your carbocation formation. This is your carbocation formation. Just have to remember nga, nanong na H2O plus man when your reactant is simply water. Again, there's the protonation step. This one is the protonation.
Excuse me, ma'am.
Yes.
Wala ka naka-screen, share screen, ma'am. Thank you, ma'am.
Okay, so you have your protonation step here. Step 0 is always the protonation step to get your H2O plus, and that becomes your reactant here. No, your H3O plus becomes reactant here to start with your alkene, the protonation of your nucleophile. Okay, so you get your step 1 and then step 3. I'll just add this one. Okay, so that's where you get your Now let's go here. What happens in one of the problems here, you know? So you have your acid, H2SO4, that's your catalyst, and then you have your nucleophile, which is H2OH. You have your alkene. So reactant here is not water, but an alcohol. The first step is always the protonation of our nucleophiles, CH3. Okay, so you have here your CH3OH is protonated, your alcohol is protonated, so may siyang positive, and then recover your catalyst. So later you will recover this one, your H2SO4 at the end of the reaction should be recovered. Whenever there is anything that's protonated at the end of the steps, this HSO4 minus now will obstruct the protonated substance here. So this is step 0, this one, and then you have your step 1 is the formation of your carbocation. After you form your carbocation here, after you form your carbocation, you have here, this is a 2-degree alcohol. So again, let's go step by step. Use the electrons from the pi bond to obstruct your hydrogen. There are 2 carbons that can form a bond with hydrogen. This first carbon here, which is CH2, and this second carbon here, which is CH. Now, according to Markovnikov's rule, we followed the carbon that contains the higher number of hydrogen. So we add the hydrogen to this one because that one will lead to a 2-degree carbocation. If we had in here, if we use the carbon to form a hydrogen here, we get a 1-degree carbocation. This is the one that becomes positive. Okay, so we use this carbon to form a bond here. You get your CH2 and you get your CH3. Since we use these electrons from the pi bond here, this carbon becomes positive. Okay, you have here, paggamit na to na the electrons oxygen and hydrogen maadto kang oxygen sa alcohol. Okay, and you will recover your alcohol, your CH3OH. So what happens again is we form a carbocation. This is a 2-degree carbocation. So this is a 2-degree carbocation. What happens is that pwede na ang, this should be the one that will, the electrons from the oxygen here will attack, to form your OCH3. But that is not what happened. Before the oxygen attacks this one, there is a rearrangement that happens. Okay, so what happened here is this is an alkyl shift, or cyclic. The carbon-carbon bond is broken to stabilize this carbocation. So again, there are different ways to stabilize your carbocation. The greater number of alkyl groups connected to your carbocation, the more stable your carbocation here. So this is a 2-degree, and then there will be an alkyl shift. Okay, what happens is kani carbon-carbon bond here, sigma bond will be broken to form a carbon-carbon bond here. Okay, you have here, and you get your, this one will be depleted of bonds. Okay, so therefore this is CH. Okay, so therefore if you have carbon forming a bond here, mahimo ni siyang carbon-carbon CH. There is only 3 bonds, so it becomes positive. And this carbon here is 1, 2. It's still a 2-degree carbocation. Okay, so what happened? This is a 2-degree carbocation. What happens is that there will be a hydride shift to form 3-degree carbocation. So this is a 2-degree carbocation, 2-degree carbocation. There will be a hydride shift to form a 3-degree carbocation here. Okay, since this one is a more stable carbocation, what happens is the O here, the nucleophile will attack your electrophile here, the carbocation. And we will use the electrons from our oxygen to attack your carbocation here. What happens is oxygen will have 3 bonds. So from 2 bonds, CH3 and hydrogen, yung katulungan bond is kaning carbon. And then ano lang siya, duha ka electrons. So what happens after you have your alcohol, this one will obstruct the proton, becomes a base, It will obstruct the protons, the hydrogen, again, utilizing the electrons, you can say. It's always the electrons that attacks, because it is the one that forms a bond. So you form a bond again, you get your protonated alcohol here, and you get your kani, you can oxygen and hydrogen, maingon pa, the electrons, you can saban maadto kang oxygen, and you will have a neutral oxygen here. That will be your product. You have your protonated alcohol, and of course you have your kani. Later you can abstract this using this to recover your CH3OH. Okay, so that is there's an alkyl shift here that happens, and here you will always, there is a shift going towards a 3-degree carbocation here, kaning part. Okay, so that is always, you always have to think of the possibilities. So usually, when would that happen? Whenever you have a carbocation, kani, and then makasilingan siya o tertiary nga carbon here. You have your carbon here, this is connected to 3R. You have R for alkyl here, alkyl. And so you can break that one to form your carbocation here. And then there is a hydride shift going on to obtain your 3-degree carbocation.
Excuse me, ma'am.
Yes.
Ma'am, I think wala naglihok imo presentation, ma'am.
Okay, so you can propose this problem is similar to this problem here. There is here you're supposed to have your OH dapat diriya H, and you have your OH. And what happens is that you have your OCH3 and hydrogen here. Okay, so you write the mechanism for this reaction. This one is a simple reaction, but a more challenging one where you can have, there's a rearrangement here. There is no rearrangement in this reaction. So I will look for a problem that there is a rearrangement, so you can practice one. Okay, so the last one is, so by the way, I will give this as a problem set, plus I will look at rearrangement problem. The last one is we have the alcohols, preparation of alcohols from alkenes using the oxymercuration demercuration reaction. And still this one follows the octet rule. So I use a laboratory procedure for synthesizing alcohol. Now, earlier we have the water, and our catalyst is an acid. But aside from water, again, I have to mention that you can also have your alcohol, no, as one of your reactant. The same reaction with water, but your product is not an alcohol, but you get an ether in the end product. This is like this one, also an ether. Okay, so you just have to replace water with HOH with another alkyl. No, but it's a similar reaction. So in this case, we'll do prepare alcohols using from alkenes, no, and our catalyst is a mercury, and this one still follows the Markovnikov's rule. You just have to remember the one that follows the anti-Markovnikov's rule is whenever we add a peroxide to our system, we get the anti-Markovnikov's rule. So what happened here is that you have your alkene, you have your water, your reactants, your alkene, of course, water, and our agent, which is usually a mercury acetate. It's the charge of your mercury here is 2+. And what happened, the first step is that you get your OH, your electrons from the pi bond, no, will attack your mercury. Mercury is a kind of like a Lewis acid, no, it has an unoccupied orbital here where it can accept electrons. In this case, from the electrons in the pi bonds, you get your Hg, and the acetate is being eliminated. So you get your electrons from carbon, you get your Hg, okay, Hg. It's like a metal carbon bond here. It's an organometallic bond here. And then the other one will get the OH. Okay, the OH, since the carbon will become depleted, you get the OH. And your acetate that's being liberated there, so H3 will abstract there will be a positive. First, there will be a positive oxygen here, protonated one, alcohol rather, and the acetate will get the protonated OH, so you get your CH3COH here. Second step is once you get this one, get your alcohol. Then we have our reactant, which is sodium borohydride, no? And you have your sodium borohydride usually abstract our proton from water, and we get our hydroxide. No? So you have your hydroxide, sodium borohydride, and what happens that it will reduce the HgOCH3 and you get our mercury. And what happens is that this one will get all the electrons from carbon here, so it becomes passively charged. The sodium borohydride will donate the hydride, and some hydride is a hydrogen with an electrons in it. Okay, remember your sodium borohydride. Nasa akong Okay, just have to remember that sodium borohydride, no, it's BH4, and you have your boron. When you have your boron bonded to H4, so boron is negatively charged now because you have your B. Okay, so if you have formal charge, boron is with 3 minus number of bonds 4 minus 0 number of electrons. So your charge here is actually -1. So you have this is your borohydride. Okay, it's -1 and positive. Okay, so what happens is that your hydrogen, your boron will donate the hydride here for it to become neutral. No? So gamitin na niya to attack your carbon. Okay, what happens is from mercury is Hg2 plus dira. Okay, to attack there, and you'll have your electrons there. Paingon kang mercury, no, and you will get actually your 2 electrons ng mercury, mahimo siyang Hg plus. No, once it accepts the electrons, and the electrons on the acetate will go there. The electrons you can hear and the hydrides you can hear, you will get your hydride here. Okay, so this is the blue one, you get your hydride and you get your alcohol here. So this is actually a redox kind of reaction. Now what happens is that once your borohydride will obtain, you actually get your BH3. No, so the boron here would have a charge of -1, and to boron, mahimo siyang 0. So it's an oxidation reaction for boron. Okay, and mercury from Hg2 plus, mahimo siyang 0. Okay, yung charge, so it becomes a reduction. So usually when you have your sodium borohydrides, it's a reagent that causes reduction to the other species. So your mercury undergoes reduction from Hg2 plus to Hg here. And what happens here is that the hydride donates, the sodium borohydride donates hydride to your carbon here to form your hydrogen. Okay, and mercury will have your freed as a p element here, the formal charge is 0. So you actually produce a metal here. Okay, so this is the visual reaction with oxymercuration here. Anyway, so still it follows the Markovnikov's rule. Whenever you get your mercury, just have to remember that this is just a catalyst. You'll always recover your mercury at the end of the reaction, and you have your HOH, you still get your alcohol in the product. So in the first step of the oxymercuration, water and mercuric acetate, you have that, and both steps. And then the second step, you have demercuration. This is a redox reaction, and the sodium borohydride reduces the oxymercury group and replaces it with hydrogen. The sodium borohydride is always the source of hydride. Always remember that. And both steps can be carried out in the same vessels. The reaction takes place very rapidly at room temperature or below. And the first step usually goes to completion. It's simply with a period only seconds to minutes. And the second step, the demercuration, requires less than an hour. It's just a one-path synthesis actually. And usually the yield of our alcohol here is 90%. So what is our reagent? Usually our reagent is that you have your mercury acetate in the presence of THF or solvent and water, and then your second reagent is always your sodium borohydride and OH or water here. And so just remember this reagent, and when you have this reagent, you get your alcohol, and of course you have your other agent, which is water. First step. So the mechanism of the, again, this one is follows the Markovnikov's rule. Example, so you have your alkene here, you get your HgOH. Your end product is you have your hydrogen and you have your OH here. It follows the Markovnikov's rule. As you have your reagent Hg mercury acetate and THF water. THF is tetrahydrofuran, organic solvent in a mixture with water. That is your solvent here system. And your water is one of your reagent. Now, this is the one that attacks your alkene to form your OH here. So prior to that, you will have your, it's not the H dione, the proton that always attacks first to the double bond. First one is that the electrons on the pi band will attack first the mercury, being a Lewis acid. You get your HgOAc. No? So the charge of mercury is still positive 2 from acetate. OAc is acetate, CH3C, OO minus this one. Okay. CH3COO, double bonds in acetate. Okay, so once you have this, you can have your second step, which is the sodium borohydride. It will reduce the mercury Hg2 plus to mercury, and it will donate the hydride. It's a hydride, the hydrogen with 2 electrons and a negative charge. This is the one that will be the source of our electron to attack our carbon here. Since when this one is reduced, the electrons will go to mercury, so depleted is the carbon, and what happens is that our source of hydrogen is Ticanderia. There should be a blue here. You get this one. So you notice that the final product here, you have HOH. So the carbon that contains the higher number of hydrogen gets the hydrogen, and the other carbon having the less number of hydrogen gets the OH, rather OH. You get this one. So here you have again your same reagent, mercury acetate, HF water. You have your alkene here, and our other agent is water. Our nucleophile is water, of course. The first one is, you have here, carbon here contains 1 hydrogen, no hydrogen rather. This one contains 1 hydrogen. Okay, so we always, the first one to follow this, to attack this one, is the carbon that contains the mercury. The carbon that contains higher number of hydrogen will attack the mercury, form a bond. And then the other one is depleted with electrons. It will become passive charge. So the water will attack this one, and you have your OH, you have yours. So let's go to the mechanism of the reaction later. So you notice, anyway, in the general, you can see you have your Markovnikov's rule being followed here. HOH, no, is being added following the Markovnikov's rule. And in this case, no, unlike the hydrogen halide and water addition and alcohol addition in the presence of acid to addition to your alkene, there is a possibility of arrangement. In this case, rearrangement of the carbon skeleton seldom occur in oxymercuration. So unlike the one that we have experienced or we have seen so far, no, in HX, hydrogen halide and water, there is possibility of rearrangement in the, when we form a carbocation. In this case, no, we don't see rearrangement reaction. So whatever you get C, you always follow the same sequence. Like for example, here you have your CH double bond CH2, no? Once you follow the Markovnikov's rule, you get your, you add your hydrogen here from water and OH from water, you get this one. When we use simply an H2SO4 as in our catalyst and water, what happens actually is there is a rearrangement here. When we add our hydrogen here, sa H2SO4 lang, what happens is that you will get your positive carbocation here. Pag get niyo si mong positive carbocation, that is a second degree carbocation. See? If our reactant is simply water and an acid, let's say H2SO4 and water, so our catalyst you have here, the first step will always be the protonation reaction. What you will get is this. Ito. Will protonate, no? So what we will get actually here is, so the hydrogen from water, it's actually the H3O plus, no? Okay, so you just have to remember that once you have your H2SO4 and an H2, it's the H3O plus, so it will protonate, will donate the proton here, and we'll use the electrons here. What we will get is carbon, hydrogen. You have your hydrogen here. Okay, and this one becomes positively charged. Becomes positively charged and you have your hydrogen here, so it's H3, okay? Because if you use this, so we'll use this one to attack the electrons. So atong arrow gikan sa pi ha, paingon kang hydrogen. Kailangan ba na ako isulat si water? Okay, sulat ka na to. You have your okay, so once you have that, okay, and you get your this. The arrow from you have your alkene will always comes from the one containing the electrons. Okay, so alkene man ang na electrons, the one that attacks our partially positive end here. Okay, always remember this one is partially negative, this one is partially positive, so electrons attack this one. And you get this. If you, and this is the one, the carbon to get this one. Of course, you have another one, another possibility, but we won't form that one because it's the one with a less stable carbocation, okay? Instead, you will get if diri ta mag-form of bond, And this kani atong positive. Maklaro ba? Okay, kani ang positive. And this is a 1 degree carbocation, but this one is a 2 degree carbocation. So we'll choose this and not this one. Okay, because this is a 1 degree carbocation. This follows the Markovnikov's rule. And what happens after actually is, what happens is that you have a 2 degree carbocation, but you notice that it is adjacent to a methyl group. Now there is a possibility of rearrangement in such a way that you will get okay, there is a methyl sheet. See, methyl here will attack the positive carbon. Okay, and you have there, and it becomes positive here. Pag shift niyo, you have a methyl sheet. You have a positive carbocation here, and then so you can add now your water. You can add now water. What happens? You'll get your water. Okay, we'll use the electrons given kang water to attack our and then you'll get your this. You get your OH. Okay, so you have your oxygen and hydrogen, okay, and hydrogen. And of course, this is the protonated alcohol. After that, you will abstract this one again with water and you get your deprotonated alcohol. Okay, so anyway, what I'm trying to say here is that after this, you will get your OH kani. Baliktad. Oops. Okay, you have your product here, but then you have a different product. So I just have to emphasize here, you get a 3 degree 3-degree carbocation. That's why you have your metal sheet to get your 3-degree carbocation. That's when the water can add here. There is what you call as rearrangement. And you get your OH here and you have it here. But what happens here is that your OH is 3 and you have your CH3. So in the case of using your mercury acetate now as your agent, so there is no rearrangement here. No rearrangement going on. That is what I'm trying to point out. Okay, so let's go to the mechanism of the oxymercuration. The first step again is the formation of your HgOAc. Mercuric acetate dissolves to form your positively HgO plus cation and acetate anion. Once you have that, so it's your Lewis acid, your alkene will react to your mercury, becomes a nucleophile. No, it's an electron rich based from the pi electrons, the pi bond deploys the electron pairs here to form a bond with mercury. And the first one is like you form a ring, like a partial bond formation. The first bond will actually the carbon that having a higher number of hydrogen to form a bond with mercury, and you get your the carbon positive charge. No, but since it is adjacent to mercury, it actually can be stabilized with mercury here to form a bond area. Get your partially positive carbon here. So once this is the alkene, donates a pair of electrons to form the electrophilic mercurous acetate to form the mercury bridge carbocation bridge here. The main bond is always the carbon to mercury having higher number of hydrogen, because you will get a more stabilized positive carbocation. But here there is a bridges form stabilized by the mercury also. So in this carbocation, the positive charge is shared between the 2 degree, this one, 2 degree substituted carbon and the mercury atom. So you have a bridge here. The next one is from the bridge, assisted. This is the carbon that is partially positive. So we use the electrons from water, that is your other agent, that is our nucleophile, to form a bond. Okay, so once it forms a bond to this partially positive carbon here, what happens is that, of course, here the electrons will go to mercury, or to form a bond here, and your mercury will form a partial positive end here. Okay, and you will have your O3 bonds to oxygen and a positive protonated OH here. Once you get your protonated OH, okay, we will eliminate the OH. The protons are protonated in mga OH here.